All right, we are at we're on chapter 30, section 30.1. The chapter is Faraday's law, and section 30.1 is Faraday's law of induction. So let's share the PowerPoint. And it starts off with a wind farm. If you've been out to, it's probably all over Texas, but parts I've seen is on the way to Lubbock. We driven out to Lubbock, and you see these wind farms, and even down to Harlingen, you see these large wind farms. And what is it about the wind farms that generates electricity? Well, we'll learn that in this chapter. But let's see. I think I went too far. Sorry about that. Okay. All you have here is you have a little wire going, just a loop connected to a voltmeter, and it shows a hand holding a magnet. Now, if that magnet were still, there would be no current induced in the loop. But once you, that shows it in that first A. When a magnet is held stationary near a loop of wire connected to a sensitive ammeter, there is no induced current in the loop, even when the magnet is inside the loop. Now, when the magnet is moved toward the loop of wire, the ammeter shows that a current is induced in the loop. When the magnet is moved away from the loop, the ammeter shows that the induced current is opposite that shown in part. So what do we see here? We see that a loop of wire in the presence of a magnetic field doesn't mean anything. It's only when it's in the presence of a moving magnetic field that you induce a current. And we'll learn through Lenz's law how to predict the direction of the current that the current will move based on the growing or collapsing magnetic field. Okay, here's a situation where we don't have any magnets. We're going to make our own magnet with a piece of wire wrapped around iron. So when you flip the switch of the battery, you make a electromagnet basically, and you produce a magnetic field. Well, that changing magnetic field will induce a current in what is called the secondary coil. Let's read the paragraphs there. The current induced in the secondary circuit is caused by the changing magnetic field through the secondary coil. I probably should have read the lower one first. When the switch in the primary circuit is closed, the ammeter reading in the secondary circuit changes momentarily. So again, it is the key word here is changing magnetic field. Okay, when a magnet is still stationary near a loop of wire connected to a sensitive ammeter, there's no induced current in the loop, even when the magnet is inside the loop. That's the same as A. And then this is the same here as the slide we just read. So what's happening? We'll see that the EMF is equal to minus d phi b dt, d phi dt. What is d phi b? Well, it is the flux, the magnetic flux going through a loop of wire. So the electric electric field, or the EMF, is equal to the minus the changing magnetic field. It's the time rate of change of the magnetic field. And if you have multiple wires, then E is equal to minus N d phi dt. So when you have a magnetic field going through the loop of wire, the angle that theta is the reference to the normal of the loop. So we have a square loop, a rectangular loop here. The normal to that loop is the vector perpendicular to the plane of the loop. And the angle theta is the magnetic field and the angle that the magnetic field makes to the normal to the loop. And we see that E is equal to minus d phi dt. Well, phi is equal to BA cosine theta. So the electric field is dependent on a change of B, A, or cosine theta. What does that mean? That means that either the magnetic field, if the magnetic field B changes, you'll induce an EMF. If the area changes, if you can somehow change the area, you'll get an EMF. If you change the angle, if theta can change, such as if it's rotating, then you'll get an EMF. You'll induce a current in the loop. Okay, now, a circular loop of wire is held in a uniform magnetic field with the plane of the loop perpendicular to the field lines. Okay, so the key word here is uniform magnetic field with the plane of the loop perpendicular to the field lines. Which, now, it's saying the plane of the loop is perpendicular. The normal of the loop is parallel to the field lines. I know that can be confusing, but you have to keep the two straight. Which of the following will not cause a current to be induced in the loop? Crushing the loop. Well, if you were to crush the loop, you would actually be changing the area. And if you change the area, you're changing the magnetic flux through the loop. So you would get a d phi dt from the change in area. Rotating the loop about an axis perpendicular to the field lines. Well, if you were to rotate it, you would be changing theta, so you would get a d phi dt. Keeping the orientation of the loop fixed and moving it along the field lines. Well, that one may be a little tricky because if it's a uniform magnetic field, it's not a changing magnetic field. Like if there was, you can see if it's on the end of a magnet, if you were to change it, well, the magnet is not uniform. It kind of grows. So if you were to do any kind of changing, you would feel it. But if it's truly a uniform magnetic field, it wouldn't sense the change. And then pulling the loop out of the field, yes, you would. You would basically have a collapsing magnetic field, a collapsing B, so you would get a change. So the only one that makes sense there is C, keeping the orientation of the loop fixed and moving it along the field lines. I don't particularly care for that example, but we'll live with it. Obviously, A, B, and D would certainly induce a current based on our E equals minus d phi dt, where D for phi is equal to BA cosine theta. Okay, now some applications of Faraday's law. This is a ground fault circuit interrupter, and as long as the currents 1 and 2, one going into the coil and 2 coming out of the coil, as long as they're balanced, you get a they cancel each other. Basically, they cancel each other. So there's a zero net flow through the ring. However, if something happened to where part of the current takes a different path, you'll get a change. There'll be a change in 2 or in 1, where 1 will be stronger. So you would get a net magnetic flux through the loop that sensing coil would sense that changing magnetic flux and trip the circuit breaker. So the ground fault interrupter works in that way. As long as 1 and 2, the currents in 1 and 2 are the same, everything stays fine. If there's a different path for the current, it senses the difference and trips the circuit breaker. Okay, here's another one. Guitar strings, metal guitar strings. Of course, this wouldn't work on nylon guitar strings, but you magnetize a portion of the guitar string, and as it vibrates, as the string vibrates, it goes back and forth into the in front of this magnet, and that produces a changing magnetic field, and it you induce a current in the pickup, the guitar pickup. Okay, and there's lots of other applications. We'll learn how speakers use a coil inside a magnet to generate vibrations. And that ends this intro. Next, we'll talk about motional EMF, but we'll stop it right here. Oops, I went too far.